Okay, good evening, everyone. Let me go through the list real quick. There's Mr. Anno. Yeah, very good. And Mr. Chen. Very good. Good guess. Mikhail. See now here, Gordita. I guess he'll show up when he shows up. Mr. Ja. Yep, there you are. Uh-oh. I'm going to get stuck here. L.E. Last name L.E. Nope. Okay. Last name L.U.I. Liu. Okay. Marcos.
Yeah.
Win.
Here.
Mr. Wang. Wang? Yeah. Okay. Good. Wu. Zhang. Zhang? Yeah, great. Okay. Guess we got one or two extras. No problem. How many of you have had this, used this room as a classroom before? So this silly monitor is set at 640 by whatever resolution. So my apologies if you hear me scream and holler and yell at it. It looks okay to you, but it looks like this to me. So I'll try my best to orient and walk you through it. How many of you have had a course where the very first day they give you everything? Well, today's your lucky day because I'm going to give you everything. I even laid out the final exam, and if I were sitting where you were, that would seem pretty tough, pretty big, pretty challenging, pretty scary, but it's not. We've got 16 weeks, and at the end of that 16 weeks, you're going to know a lot more about reservoir engineering than you ever imagined. Hopefully you know a little bit more about the analytical solutions that we use for classical reservoir engineering, and hopefully you're really feeling good about using some of this for your research. Now, every time I start to teach this, I think about the things that I wish I had put in, the things I didn't do. And I guess when you get old, you start thinking about the things you didn't do. We don't cover horizontal wells. We don't cover horizontal multifracture wells. We don't cover some of the other things. Why? Because that's just too damn much. You know, by the time we get to all that, you'd be vegetables, you know. Now, Mr. Jai, you had the course with me this summer. You had 3 courses in one, right? You had Mr. Kennedy, Dr. Schechter, and then myself. How'd you like that? There was like 3 races.
Yeah, I was taking one more class.
And at the end of it, you were completely exhausted, you were angry, a little frustrated. How'd you like the final exam? It was way too easy, wasn't it?
Similar to what you gave us.
Sorry?
It was similar to the papers that
It was exactly, it was completely different problems, but I said, well, let me do this. Let me see if they learned what I told them to learn. And the average was what, an 88 or something, you know? So, yeah, I broke my mold. I usually don't have averages even anywhere in that orbit, maybe if you squared the number. But that was okay because everybody achieved the goal we laid out. And if everybody gets an A in here, that's okay. You have a reading assignment. You have a series of homework assignments. The reading assignment is not fun, but it's designed to, you know, keep you on your toes. And some of it's going to be a little bit of a distraction. Some of it's going to be just plain weird. Why? Because I got to mix it up. I got to make you think about reservoir engineering from all sorts of perspectives. And then the homework assignments, they're all from the notes. There might be 1 or 2 problems that aren't, but come on, let's be fair. You can handle that. So all the problems are solved problems. So right there, that's 30 points plus 50 points. All you got to do is reproduce it, more or less. There's a lot of work that goes into it, but you got to reproduce it. And then the final exam is Van Everdingen and Hurst, 1949 paper. And you don't have to rederive anything because we're going to do that elsewhere. But you actually have to calculate something. And I want to see what you can do. I was at you'd call it a forum, they call it a colloquium, 2 weeks ago. And we were talking about the skills that industry values. And I thought, oh God, here we go again. You know, too much hard skills, too little soft skills. Academia doesn't know what it's doing. You know, and then the academics are all going to say, well, you know, we create a product that takes 4 years and you guys don't understand, the industry changes, and then, you know, the subject of graduate students comes up. But something really remarkable happened. It really was. People started talking about what differentiates an average or, you know, a strong performing engineer with a superior performing engineer. And maybe it was just a moment. I don't know. But what do you think differentiated the sort of good from very good or very good from great? It shocked me. And the conversation started sort of rumbling through the almost 100 people there. And it was the industry guys telling us this. What do you think it was? Nobody? Take a shot. Wild guess. How you cut your hair, how you wear your shirt, nice clothes, what? What do you think it was? Nobody. Not even gonna guess.
Communication.
Sorry?
Communication.
In a way, directionally, that's true. In a way. But it was actually mechanical. It really was. Jorge, what differentiated your experience this summer from you and everybody else in your internship? What do you think made you stronger than the people around you? Or maybe it didn't. I don't know. See, you walked in late, so I get to torture you a little bit. Okay.
I guess
What did you do all summer?
the planker.
Okay, but what did you do? What did you do every day?
What do you mean by planker?
What is this, Bill Clinton Day? Come on. You were on a computer.
Yes.
You were doing what?
I was trying to code whatever I.
Code.
Yeah.
Coding, programming, whatever you want to call it, was the differentiator.
Yes.
I've never heard employers, people from industry say this before. Undergraduates and graduates. People who can take information from one system to another, somehow, where it's not seamless, move it, and do the problem solving on their own. I was surprised. I felt like the last 35 years of my life had been spent waiting for this moment. I haven't taught or required programming in this course for almost 20 years. Why? What do you program in? Let's go down the list. Favorite program?
Mathematics.
MATLAB? Okay. How many Mathematica? Okay. How many Fortran? There actually were a few. How many VBA? How many Python? How many R? One. Okay. You see what the problem is? What tool did we require? So how many of you are taking Dr. Gildine's class? Anybody? What does he require? MATLAB. Take Dr. Maridi's class, what does he require? Fortran. Take Dr. Valco's class, what does he require? Doesn't matter because he's retiring, right? But, okay, but what does he require? Mathematical. Dr. Maggart? 665, DBA. So what do we do?
You require all of them in the test.
Oh, God, I like you. But that, unfortunately, is probably going to be the reality. But I hope that we could kind of coalesce on one thing. Jorge, why did you work in R?
I work in R because I presented as a free tool for everyone, like an open source.
I just was curious because I was talking to someone and the data system, it would be indiscreet for me to say the name, but it was Halliburton. And they were recording data every second. And they were sending the owner, the operator, a file once a day with that data in it. And it was tied to clock time. And the date was printed in the top of the sheet. But there was no date over here. How many seconds are there in a day? 86,400. So this well's been online for, let's make up a number, 100 days. So something like 10 million data points. How are you going to reconnect that? And I know what you're all thinking. You know, your generation says, we know the data is stored on the device. But getting Halliburton to go back and pull 10 million data points and somehow send it to you, how are they going to do that? You may be waiting a while. So this guy took the data, put it into R, and reconcatenated it all, and sent it to me in a text file to look at. That's the hard way to do something. But that's what people are going to have to do. And it would be nice to tell you that you're never going to have to do that, but you're going to have to do that. How do you process data? How do you make computations? How do you set up problems? The difference between now and 30 years ago is we only had programming languages. Now you have numeric symbolic tools, Mathematica. Why don't we just all use Mathematica? There was a moment about 15 years ago when I hesitated. You guys know what hesitate means? I saw Dr. Valco going that direction. I said, I'll go that direction. Okay. How many people are employed by the company Total? Anybody know? Something like 102,000. Okay, something like that. This was a while back. How many copies of Mathematica do they have in Total? Wild guess, anybody? One. Very good. Where's the candy bucket? Yeah, pass the candy bucket to her. She's gonna. So you can't really rely on Mathematica. Although there is a very interesting thing now. Have you guys used Wolfram Alpha? It's a free tool. It's Mathematica Online. And if you buy the Pro account, what I love about it is it's Mathematica Online, but whenever you start to solve something really tough, what does it do? Is you need more credits. Credits? Credits? I already paid for this thing. Okay, but of course, that's a business model they have, so we'll just say that. What about Python? What are the limitations there? Where are our Python users? What are its limitations? What's your thought? I mean, what kind of problems would you not want to solve in Python?
It's very convenient, but I won't use it to build a simulator because it's slow.
Okay.
Slower than C++ and Persian.
Okay.
Yeah, I guess I haven't worked on a bigger problem. Till now it works just fine because it's similar to MATLAB. So I was working also before on MATLAB, so I didn't find any problems till now.
Anybody else want to throw anything out there? You know where this is coming, right? The way I do things is I blow it up and then I bring it back. Go ahead.
Python doesn't work very well with Windows machines.
always rely on the Russian. Well, thank you. Very good. Where are we converging back to? What does everybody have? Excel.
So I'm sorry. My question is, shouldn't be this collaborative work between developers and reservoir engineers? I believe that we should know more about programming language, but we don't have to have this wide knowledge about all the language, all the programming languages
No.
that are there.
But my point
each
is
company
you will use the tool you're most comfortable with.
Yeah.
And what is going to happen? You know, I've said this for 25 years. The most important problems in the world will not be solved in Excel. But that's the tool that everybody has. So
Yeah.
what motivates you to move to another tool?
So no, actually, so while I was shifting, this shift happened because different companies use different language. So that's why I need to shift between MATLAB to Python. So at first that I was using MATLAB during school, and then after that I need to use Python. But as you said before, that every company uses a type of programming language. So my question is, shouldn't we just have a fair knowledge about this language, but we don't have to be expert in that, because I believe that most of the problems that we face in reservoir engineering can be solved away from the programming itself. Yeah, so
I agree with you, but then what happens when you have these huge data channels that are going to have to be communicated to the software you want to use? I'm not advocating that we suddenly decide that we're going to program everything. This is class. So in school, yeah, I can say we are going to do this because it will build, you know, it's like climbing stairs for exercise. Nobody likes climbing stairs for exercise, but it damn sure works. You know, so the next question is, what do you do in the real world? How many people, when you're sitting in your office complex, how many people are actually thinking about how to solve a problem, and how many of them are using software? And the more time you spend watching people use software, the scareder you will be. I mean, right now, my biggest fear is with the recent round of consolidations, and I say this in absolute honesty, I would say it in front of the people that I care about, but we're basically down to one vendor in reservoir engineering with production analysis or pressure transient analysis, etc. Guys, every time you have a monopoly, something's going to happen. So, you know, next semester, I'm going to have you guys build your own sapphire, topaz, whatever you want to call it. Why? Because you have to be able to understand how to build those tools so you can compete. Someone, perhaps in this room, is going to come up with an idea to compete with reservoir simulation or something else. You know, that's what school is about. But I was just surprised, and I'm, you know, already taken up 15 minutes, talking, you know, with these guys from industry 2 weeks ago, that they really felt like programming was a differentiator. The ability, not the act of it, but the ability to link things together. Now, the only programming assignment you really have in this class is going to be the final exam. You're going to have to calculate those values using numerical inversion. And I've recommended, actually I've stated that it'll be the so-called Stayfest algorithm, which is the simplest algorithm. Dr. Valco has an implementation in Mathematica that's extremely accurate, but it's extremely tedious as well as time-consuming. I don't know, I have forbidden you from using Mathematica for that problem, by the way, so, you know, let's just cut to the chase. You're going to have to do something different. Excel will work, and you will have to work around it. I'm really surprised about how, you know, classic problems still present real challenges to people. So let's get your skill set built up that way. Theoretically, you could probably finish this course before October 1st if you wanted. I wouldn't recommend it. I mean, I think the lectures, as boring and as dragging on as I am, I think they're going to be meaningful to you. I think we're gonna have a good time. We gotta figure out how we're gonna do classes. I have a horrible September, and I apologize for that, but a lot of SPE travel. I roll off the board on the 26th of September at 4:59:59, and we will have a celebration, I'll tell you. But that's a month from now, so I gotta do what I gotta do in between. So we'll have a bit of a bumpy lecture schedule this month of September, and then inevitably there'll be some other travel that comes up and so forth. But we'll get all our lectures done. I would like for I'll talk to the guys that Jorge's obviously going to TA for me, and I have another student as well. I think they would like to do the math lectures, which is fine with me, and certainly they're as familiar or even more so than I am, so they can give you the kinds of pointers you're going to want. No one's really asked me yet what the purpose of this is, and it is unfortunately like building a road through the jungle. This is your road. This is your path. I'm your guide. I'm not going to let you die. I'm not going to let you get killed. I'm not going to let anything bad happen to you. But I'm not going to carry you unless I have to. And I don't want to do that. That's not really my favorite thing to do. So, we'll go start from very fundamental principles in reservoir engineering, work our way all the way through, and then we'll come to the end, and I think you'll feel pretty good about it. I am impressed. This thing is recording, but our course is not on eCampus. So I have no idea where this video is going, but anyway, I have a backup, so it'll be fine. And I guess everybody got my email tonight, so that's good. That is the only one I will send personally, at least until we get back on. So this is all a bunch of junk about me. Sorry. This is about you. So you will need to buy these two books. And I see someone already has one. And it needs to be the 1971 version. Okay. So 1971 version. Congratulations. And then Jaeger. Now, I can't say in a lecture that's being recorded that you could find all this stuff on the internet, but I'm sure some of you would already know that. But I think it's a good idea to buy these books. These are things you're going to use the rest of your career. I'll tell you a little secret about Jaeger. It's like a treasure map. Jaeger and this textbook by Muscat, sorry, I'll have to point it out. This one you'll have electronically, but these two you'll have to buy. If those guys had had a computer, we wouldn't be here. They pretty much solved every problem we ever thought of before we thought of it. Yeah, they didn't do horizontal wells. Oh, yeah, they did. Yeah, they didn't do fraction. Oh, yeah, they did. They pretty much did everything. Now, maybe there's kind of screwy and you have to, fix a few of their geometry or setups or maybe some of the boundary condition things, but pretty amazing. Those two books pretty much have everything we could want. I like for us to go down a discussion as well about things like special functions. So I'll often talk about the Abramowitz and Stegan. Abramowitz and Stegan was also an early 1970s book. It was produced by the United States government. It primarily consisted of being a resource for certain accuracy of numbers. It's not necessarily going to be to 100 decimal places, although there are some numbers in that text that are that. In a way, software like Mathematica has completely obliterated things like Abramowitz and Stegan, but it's still there as a physical reference. The table of Laplace transforms by Roberts and Kaufman is absolutely amazing. You're going to use it, so you'll get to know it. Numerical Methods by Hornbeck is just a really good, rock-solid numerical methods text. Approximations for Digital Computers, this was Hastings. Look at the date. This was 1955. And in 1955, how did computers make calculations, class?
Of course, on paper.
Sorry?
I said on paper. It's not.
Okay. Anybody want to guess?
Light bulb?
Sorry?
Light bulb?
Okay. There were switches, yeah. But, I mean, how did they make, okay, so right now you push a button on your calculator on your phone and you say cosine of x, somewhere it goes and finds cosine of x. Do you know what it does, or do you care?
Is it like find linearity?
Used to be perforated pieces of paper or something.
Okay. Sorry.
Is it like a binary, like 1 0 1 0?
Okay,
kind of
she's
thing?
on the right track. Yeah, there were all sorts of analogs, but what I was getting at is when you push cosine on your calculator, what is it doing? It's going to find the equation that that company uses with the precision of that device, and it returns a value, okay? But that equation is made up of what operations? Addition, subtraction, multiplication, division, exponentiation, and logic, the on and off. And that's all you got. The universe is polynomial, okay? Plus, minus, multiply, divide, and an exponentiation. Look sometimes, go look up the algorithm, just type, you know, algorithm to calculate, I don't know, cosine in Fortran. And it'll be this long, and it'll just be nothing but coefficients to an equation. Okay? Where did those come from? They came from here. This was the first book on how to calculate something. And it, to you, it's going to look almost silly because it tells you how to calculate e to the x. It tells you how to calculate logarithms. Why? Because it didn't exist then. So this is really good. Now, follow that by the handbook for computing elementary functions. And I apologize, I'm not going to be able to pronounce this guy's name correctly, but this is the Russian version. Now, in the West, people were using sort of statistical methods to estimate functions, curve fits, if you want to call it that. And when you read the Hastings book, it's going to talk about how these different functions are approximated. And when you hear approximated, you have to think. There's an equation. How did the Russians do it? Okay. What does Russian, the word Russian, translate into in English? Does anybody know? The hard way. Okay. Is that right? You have to do it the hard way. So the Western book is about that thick, and admittedly it was written 10 years before. The Russian book is about that thick. And it's all sorts of asymptotic expansions, series expansions, splices, everything else. I mean, it is the most elegant, the most brute force method for making calculations. Who won? The most accurate. You have to have these calculations at machine precision. So we'll talk some more about that as well. The flow of homogeneous fluids and porous media is Muscat's book. And we'll more or less stop there in terms of the books. That one is the, I don't want to offend anyone, that's the holy document for reservoir engineering. 1946, originally written in 37, if I remember correctly. But second printing was 46. Amazing book. Amazing book. And if he'd had a computer, we wouldn't be here. So. Okay, as I mentioned before, well, First of all, everything's on this site. Don't forget it. If you do, just type my last name and the letters PE somewhere and it'll pop up. Reading portfolio, there are 30 reviews for 30%, so each one is a point on your final grade. Homework portfolio, there's 50 little problems, or actually not 50, but maybe 40. A couple of them are worth 2 points. And then the last is the Van Everdingen and Hurst problem, that's 20%. So just filling in the blanks, so to speak, is 80% of the class. And this little task is actually really easy as well, but it's going to take some time, and it's going to take some effort. Okay. Due dates. Why do I make these due dates different? I had a professor named Ching Wu, and Ching Wu was one tough guy. He came to Texas A&M from Colorado School of Mines, and his first semester, he failed half the senior class because he didn't think they were very good. And this was 1980, when you could get a job if, you know, you had a D+ average, and he failed half the class. So next year, because they only taught the courses once a year, he came back to class, and what did he say when he looked out? He said, "I see lots of familiar faces." He was a tough guy. And he stopped me one time. We were going to lunch when I was a young faculty member across the street over at University Drive, sort of close to the Methodist Church. Traffic buzzing by us. And he said, "You know, Tom, the only thing you can't change is human nature." What's human nature when you see a date? Don't worry about it till then. You know? Dr. Lee, my advisor, used to tell me that nothing's important till the deadline. That was really bad advice. Okay? So I staggered them, just so you'll get them done. Okay? I think you'll do fine. Okay, all this other stuff is just nasty words telling you not to misbehave. Sorry about that. Here's some other nasty words about things you have to do. You're going to have to type everything in here, so go on ahead and get that into your head. Sorry if that offends anybody, but no more handwriting. We really suffered recently with people's handwriting, so everybody types it. And I would prefer that you use a normal font, not, you know, it would be nice if you use Times New Roman. Please do not use Courier New, okay? Courier New is my email font, everybody, not my writing things font. I've asked you to use this protocol. How many of you have used this before with me? At least a couple. Yeah. Or it's like, I don't like it, but I will. And why? Because I save everything on a student's name basis. I've already created folders for several of you. If your name is in the subject line, I can sort, I can find, I can drop. Makes me a lot happier. If not, I'm really not happy. Number one rule is do not reply to my emails. Start over. If I'm sending an email to the class and you say, "Hey, you know, I'm just in a hurry, I'm going to do this." You guys remember Yosemite Sam, the cartoon character? Yeah? No? Maybe? Okay. He would explode. You know, okay, the movie Mars Attacks, when their brains explode, that's what that does to me. So, and please make sure you do exactly like I ask. Again, I know this is really stupid to waste 2 or 3 minutes of class time on this, but we're going to have a lot of correspondence. And you're going to get lazy, you're going to get sloppy, and it's not going to be pleasant. So please do that for me. Okay, computational tools. I think we already pretty much talked about this. I'm not going to tell you what to do. Sorry, rephrase. I'm not going to tell you how to do it or what to use, but, you know, life's tough. Now, unfortunately, this is kind of tricky because I say I don't really care about Mathematica, but on the final exam, which is the only place you really have to make a computation, I tell you you can't use Mathematica. It's okay. I can be self-contradictory. All right, here's all the good stuff. Here's our outline. First couple of weeks traditionally was a review. Again, I may defer to the students. Then we'll talk about petrophysics. Then we'll talk about fundamentals of fluid flow and porous media. And I know all of you, Mr. Jha, you remember whenever we reached that point in the previous class where you were all just tired? This is going to be that point. I used to love getting to the multi-phase diffusivity lecture because people just didn't care. It was like this mind-numbing experience of deriving this thing. And about 25 years ago, I had someone in the back row go, "Ah!" Oh, I get it. These are the same equations we use for reservoir simulation. And I said, oh, that was the goal. Very good. Thank you. So we're going to derive all of these. And then here comes the classic reservoir solutions. And this is where sort of I can't afford to lose any of you. I know the algebra's tedious. I know it's ugly, but it's doable. Jorge, you got anything to say about this? You didn't like it, I know, but it was okay. It's just part of life. You got to do it. There's a lot of knowledge. There's hundreds, if not thousands of years of knowledge buried in that. A lot of people's lives' work went into these things that we now take for granted. We need to work on that. We need to convince ourselves why. You know, the irony of that conversation that I was telling you where people said that they really liked people who could code, people who could program, people who could have independence of thought on problem solving. Another thing they said they really liked was extremely strong foundational skills. Extremely strong foundational skills. So that's what we're going to build here. And then these are just some extra sort of little discussion things. Now, I'm not going to cover everything in the syllabus, but this is our order. There is an old sequence of lectures, and these are all in what's called the base lecture folder. So these were the original lectures for this. I've created sort of a PowerPoint version of these. Some are very similar, some are not, but these will be sort of 8.5 by 11 or a portrait type files. Some of them will be hundreds of pages long. They'll have the papers in it. They'll have some other things in them. But if you really are motivated, and hopefully you are, you'll follow along these lectures as well. We don't have class on Thanksgiving. We do, well, doesn't affect us, but we do have a football game this week. And then these are all your final things. Anybody graduating? Tell me now, please. Nope, good. I like that. Yeah, that's sometimes you lose weight and hair whenever you work on that. Your grades will be due on the 17th. All the assignments are due on the 10th. I mean, you know the due dates, but the final exam's due on the 10th. And then I have the assignment cover sheets and the assignments already done. So here's the reading portfolio. And for the reading portfolio, you'll create a single page. Don't put them. It's one page per review. Okay. Maybe I didn't make that clear, but don't string them all together. Devote one page apiece, and then tell me, what was the problem solved? What are the assumptions, limitations? What are the practical applications? Blah blah blah. Now, doing just the minimum is absolutely fine, but if you do less than the minimum, or you start to show that you're not doing anything, the grader's going to figure that out. And the graders, they go from really nice people to really not nice people when they figure out that you're not doing what you're supposed to do. And if they're not nice, you can imagine I'm not going to be nice at all. So very simple setup, just bullets. Tell me what it was about. And, you know, if you're thinking, well, just copy what the guys did last year, probably a really bad idea. Because I keep a copy of everything everybody ever does. That's my OCD. And I changed up about a third of it. Oops. So you'll have to do it anyway. Now this is worth approximately 1/3 of your grade. How hard can it be? Well, unfortunately, this is how hard it can be. So here are your 30 articles that you're going to read. Some of these, relatively easy. Some of these are going to be voluminous. They're going to be a book. I don't expect you to write any more than is required for a review. I do not expect 2 pages. I want 1. I do not expect 20 bullet points. I want whatever you're comfortable with. Some people did a fantastic job on the reading assignment. Truly, I have to say, commendable job on the reading assignment. Some of the best work I've seen in my career. If you want to do that, that's great. But still only 30 points. So don't do that and sacrifice something else. But again, that's why I staggered the due dates. So, a lot of things in this. A lot of things in this. I took some of the papers out that overlay exactly what we're going to do in lecture. Okay? And I added some things, I changed some things around so that it would give it a bit more breadth. And it would give you a lot more perspective. Reading Muscat's book, reading Pearson's book, reading Berg's book. You know, I'm not asking you to read it, you know, line by line, but I'm asking you to get a feel for what was the author thinking? What are the similarities? What do you believe really applies? What do you don't? Okay, excuse me, sorry I jumped too fast. And then this is the roster approximately of, where these would fit, so approximately. So you know, you don't have to read them. You can read them in order if you want, or you can sort of read them following along the topics. But the Tom book and the Van Weer book, you can see they're extremely old. They're still really good reads because they were unique perspectives at the time. And then you can see working our way down, we get to things like petrophysics, and there's some background material, some sort of general knowledge stuff, and then we get to correlation of petrophysical data, and it gets really heavy. I don't mean for it to get heavy, but there's some really good work out there, especially on things like unconventionals, where you go to ultra-low permeability, and those are the kinds of things I also want you to see. I was going to take the Klinkenberg paper out, for example, but then I thought, well, you know, you can't have a class on flow-through porous media without having the Klinkenberg paper. This was written in 1933 by Fancher, Lewis, and Barnes at Penn State. What was 1933 like? Was it a good year? Anybody remember? If you had to sum up this particular work, and it's about 100 pages, what were they doing? They were trying to show the relationship between pressure drop and rate for about a zillion different materials. Now you would call that what? Darcy's Law. But they instead tried to make a friction factor Reynolds number plot out of it. And guess what? There's a lot of non-Darcy flow out there. We don't see a lot of it, but in the laboratory and in certain materials, they did. And, you know, sometimes it's about language. They created the first Reynolds number friction factor plot, if you want to call it that, for flow and porous media. And if they had done it correctly, what would have happened? All the trends would have overlaid. But they didn't. Why? Anybody know? That's the whole point. They used what they knew at the time. They used what they knew for Poiseuille's law for flow in pipes to define the Reynolds number and friction factor. But that doesn't apply. So when they use Forkheimer's equation, 25 years later, 20 years later, whatever it was, that was Cornell and Katz, all of a sudden a universal correlation emerges for flow-through force meter. Pretty clever. All of this work that we do in petrophysics really comes around Archie's work. It says 1950, but most of this was done in 1942. And then there was some other work later on by Waxman and Smits. And what Waxman and Smits showed was that the shale content of different formations severely affects the electrical properties. And then a fellow by the name of Wiley, and it was Wiley and Spangler, they did a lot of work on this. They were very determined. In fact, I think it was kind of a competition between them and Archie at the time to see who could prove or disprove each other's work. A lot of really interesting stuff going on. And then the so-called homework portfolio. So what does solve problem mean? When you see the word solve problem, what does it mean? It means it's worked out. And so people go, well, why do I have to redo it if it's already worked out? Okay, I can go find a bunch of problems that aren't worked out. But I thought you might like to see how it is worked out, rework all the steps plus anything that's missing. And by the way, even in books, there's an occasional error. Okay, so it might be a good idea to do that. And then I really like this section in Hornbeck's book on how to do least squares. Because every time you use Excel, people right-click on the data, do trend line. What is trend line actually? It's this. Okay. And what is solver? Well, solver is a lot harder. If linear least squares problem is this big, nonlinear least squares problem is the rest of the universe. You know, it's gigantic. So we have to learn how to do sort of the linear case or the linearized case, if you want to call it that, and then we can do the nonlinear stuff. So next is some more solved problems, and then we get into derive this. Now before you have a heart attack, all these derivations are already done. There might be a mistake. There might be a missing step. There might not. Who knows? That's the beauty of it. But I need you to do all these things. This is building your strength. Okay. And you can see that each one has a number of points assigned to it. And we keep going. We have the fractured well case, naturally fractured reservoirs, convolution, wellbore storage. You know, I should just tell you, if you can solve this one, then you can just have an A in the course and don't come back. Okay. But if I say that, somebody's going to do an all or nothing, and something really bad's going to happen to them. So don't do that. Okay. This is an insoluble problem. What happens with wellbore storage is you combine two conditions, the wellbore and the reservoir, and it looks so easy, so elegant in the Laplace domain. But that's the whatever you want to call it, the treachery of the Laplace domain. Things that look easy in the Laplace domain do not invert. Like the reciprocal of a logarithm plus something that is not going to invert. Now you're going to say, well, we could approximate it. Yeah, and some of us have spent the better part of our, young life coming up with approximations for that. But I'd like to see it done, directly. So, at any rate, if you could directly solve this, you get a free A and don't come back. Don't do that. I don't want the responsibility of that. Okay. Here's your final exam. Your final exam is this equation, which we derive. Equation 6-4, equation 6-27, equation 7-4, equation 7-11, and then equation 8-10. We derive all these in our other portions of the course. This is back in the radial flow derivation, and then the last one is in the convolution / wellbore storage relation. That paper is now 70 years old, right? Will be next year. And there's still things in it that just boggle my mind. They solve things that we just hadn't thought about. So, I want to be honest, this will take you a weekend to do, but it'll take you longer than that to do right. Okay, so you've got, I strongly recommend that you wait until after we cover the development of these solutions and their real domain solution before you attempt this. Or do it synchronously, do it at the same time, but don't try it now. And that's about all I've got. So, I mean, the rest of the syllabus is in here, and it talks about all the different topics we're going to cover. You got your first date, you got your syllabus, you got your homework, or sorry, not your homework, but your email protocol. I also ask you to give me your resume. And did you guys look that up yet?
Yes.
So, just give me a one-page version of yourself. Obviously, you know, there's some method to my madness. I want to get to know you. I want you to get your resume in order, because next week is the resume workshop, and after that is a career enhancement event, and you need to be ready. You need to do these things. So, you know, did you look at it? Yeah. What did who was the picture of?
It was like a guy, John.
Yeah. It was Jim Smith.
Yes.
You'd be surprised when you type Jim Smith photo how many millions of Jim Smiths there are. So I just cut and pasted one. I'd like to get a photo of you just so I can, you know, put a face with a name. I know you're going to go, that's sick, Tom. I got it, okay, but I still, you know, need to do that. Jorge, anything else you want to say? Okay. Any questions? I would like to meet probably Thursday night as well. I know we meet Wednesday, and I'll try to make, football game. Forget it. You won't even be able to get on campus, so forget it. We'll talk about it later. I'm trying to rearrange travel so I can be here on Monday. How many of you are new to Texas A&M? Completely new? What is Monday? Yeah. And everywhere else, Labor Day is a non-Labor Day. You don't work. Texas A&M, you do. Whenever there's something that you don't like at Texas A&M, they always say, it's a tradition. It's a tradition. We have school on Labor Day. So, unfortunately, I'm supposed to be traveling that day, and I was going to see if I could swing it. I may not, but regardless, you know, I'll get my travel schedule together, and I will tell you when we're going to meet. Jorge and Rui will probably take care of the math lectures. I assume you guys want to do that. I don't know. Rui and I haven't discussed it yet, but well, Rui and I talked about it, but I haven't really laid anything out. So. And then we'll see a lot of each other. I just want to apologize in advance. You know, I really do not like to teach remotely. It's really hard for me. I need to be able to see you. I need to be able to yell at you. You know, I need to be able to know what's going on. But there probably will be one or two instances where I have to do that. Have the tools. I just don't like it. I like to be here. So there is a real possibility September we may not see much of each other, but I'll do my best. I know travel back here for a couple days, travel back here for a day, travel. We'll do the best we can. And we're going to have a party on September 26th. So, last day. How many of you are planning to go to the SP fall meeting in Dallas? Nobody. 1, 2, I see a couple of fingers. All of you should go. Why not? You know? Just try to go. Things are picking up. Life's going to be pretty good. What's going to happen in 2022? Anybody want to guess?
Will the train from Houston stops by Constitution to the Street
Oh,
Palace?
I thought you were going to say something about Trump, but okay, I got it.
Will the train?
Best guess is 2022 is when we're going to, all the surplus of graduates is going to be consumed by the system. And we're going to have another shortage. And I shake my fist, not at God, but at the sky. Because when this happened the last time, it was unpleasant. And you're going, we're okay with it. Yeah, we'd like to see that. Yeah, I know you would. And I want you to. You know, but just get ready. Here we go again. And, you know, it may not happen quite that way, but other schools have extremely low enrollments. Our enrollment's a bit high, but it's because we're us. And, you know, it's going to be some very interesting times coming up. Questions before we go? Where's the candy bucket? Everybody get some? Yeah. No? John, you had enough? No? No more? What is this book? Ah, you went and got it from the library. Good girl. What's going to happen now is everybody's going to call it. They're going to make a request for it.